So in class, we also talked about the LP norms, specifically the 1 norm, which is called the Manhattan distance, and the 2 norm, which is called the Euclidean distance. These have different names that we'll see when it comes to regularization. When we apply L1 to regularization, that's also known as lasso in the in-class notebook, and L2 is known as ridge regression. And as we highlighted to you during the in-class session, this is because machine learning inherits from several different fields, including computer science, but notably statistics. So statistics has contributed these terminology from before, and that's also why a lot of the variable names are different. In any case, let's look at the LP norm. The LP norm, as it's stated here, is just denoted with double bars in most cases, with a subscript p denoting which power of p we're talking about. For us, when we take the p value equal to 1, then we get the Manhattan distance, which is that we have a power of p to the first here. And it's just basically the sum of all of the components of x. When we do regularization, this x will be replaced by theta. So this is going to be a constraint then on all of the theta from feature 1 through n of their sum. So their sum cannot be greater than a number. If we think of this grid as theta 0 and theta 1, then what L1 regularization is doing is saying that there is a cap on the total amount of weight that is in the buckets for theta 0 and theta 1. For example, if I put it here, that means I'm putting 5 units into theta 1, and if my budget is 5, that means I cannot afford any other weights for theta 0. And similarly, if I go here, this means the same. I have a budget of 5, so all of these red points that I'm drawing here have a budget of 5. Right? Because either way you look at it, I can contribute either a positive value in the y direction, which is going to take away at least 1 unit of the x direction. So we'll have this type of border shape. So this is L1 distance. We call it Manhattan distance exactly as it says here because it looks like square blocks, right? You have a total number of budgets of blocks, and whenever you run into the border, you've used up your budget. Okay, so we'll understand that. Let's look at L2. L2 you've seen many times, so I don't think we have to explain this a whole lot. This is just Euclidean distance, which means we take the square of whatever proponent you're putting in here. Normally when we're doing regularization, it's again about weight, so we'll take the square root of the sum from I equals 1 to n of theta I squared. So I'm going to sum up all of those and take their square root, and that's going to have to be less than or equal to some budget c. Right, that's what we mean by regularization. What we can think about for L2 regularization is that it defines a radius of a hypersphere that's at that point. So if we have 1, 2, 3, 4, 5, 6 units of length would sweep this circle out like this. So in the previous part in the post lecture, you saw that when we were thinking about regularizing using weight decay, which is exactly L2 regularization, we painted a red disk around, right? So that's the geometry of this. So with the LP equals 1 and 2, we get this type of visualization for it in 3 dimensions. We have a hypersphere and a polyhedral for p equals 1. So this is in the case where we have 3 dimensions where we might have internally an x, y, and then some z in another dimension. When we have a p-value that's less than 1, it's not exactly a norm because it doesn't obey the triangle inequality, which a norm does. But we can think of it as spiny type of polyhedral that when we set to 0 is basically going to constrain all of the weights except for 1 to be 0. Okay, so it has this spiny skeleton shape, okay, in 3 dimensions. We can also increase the size of P to an infinite amount. Somewhere in between, it would look between a sphere and this cube. When we have P equals to infinity, this is also called the max norm, and you should be able to figure out what type of constraint a max norm constraint means when we have a shape like that. So we also talked about the properties of the geometry of different regularizers. We said L1 is set to encourage sparse solutions, pushing certain coefficients of theta to 0. And we can use it to do what we call feature selection. So if we have a whole bunch of features, let's say x0 through x100, what will happen is that using L1 regularization, some of these theta values, their associated thetas, are going to often be pushed down to 0. Okay, and what that does is it basically cancels out that feature. If I have a feature, let's say xn here, where its theta n was pushed to 0, it's going to be multiplied by 0, and that thing just goes away. So the end result is, even though you might have started with a high number of features, some of these features will just simply curl off to 0 with this 0 weight, and they'll become negligible, right? So it's basically saying that you're working with a feature space less than the amount that you put in. That can be very good for us when we want to discard features that we don't think are helpful and that embody high frequency noise rather than any signal. So how does L1 actually do this sparsity? Well, it's quite informative to look at the geometry. So L1, as we saw in the Manhattan distance part, will give us a border that's a polyhedral like this. And this is because, again, we can either use the budget for x0, in this case on the y-axis, or trade it exactly 1-for-1 for a unit in x1. So this is a two-dimensional plot of just theta 1 and theta 0. Okay, I'll just replace theta here so it's easier to understand. And then we are just trying to choose a value of theta that's going to help us achieve the best possible training cost. And we know from linear regression that we can do this by either a closed form solution or by gradient descent. We're going to call this solution, again, theta lin. And if we cannot reach theta lin because our regularization constant C is not big enough, it's going to intersect with these contour lines that represent equal cost at some point. And you can see what happens here. Zooming in a little bit, you can see that the point in which the ellipse of the least amount of cost hits the polyhedral is at one of these intercepts, namely this intercept here. So what's happening here is theta 0 is getting a value, but theta 1 is getting a 0 because it's on the line x equals 0. So this means that in this case, the feature x1 is being thrown away entirely. So it's getting a sparse solution by assigning all of the weight into theta 0. So this has a nice intuition for us, right? Because what it is basically saying is that by using the geometric shape of the L1 being this type of polyhedral, it's very easy for cost contour to bump into one of the corners aligned with an axis for L1. And that means it'll put all of its weights towards certain features and turn off other ones. So here again, theta 1 is being turned off and theta 0 is being assigned the full cost. What about L2? We say that L2 can be used for regularizing homogeneous data. What do we mean by this? We mean data that comes from the same source. So for example, in a loan application, we have features that come from very different sources. We might have some inputs that represent the gender of the client, the age of the client, how many years they've lived in a current residence, what's their current salary. All of those are not very comparable items. Okay, so in this case, we wouldn't want to use L2 regularization. Where we would want to use it is in the case of something like features that have similar values. So for example, in an image regularization problem where the image data are all features of raw pixels, those pieces of data are all comparable to each other. They're of the same type, and L2 regularization makes more sense there. Why do we say it makes more sense for homogeneous data? Well, look at what L2 does. L2 has its constraint set as a hypersphere centered at the origin. So any place where it touches the sphere is the optimal region. And you can see here it doesn't really encourage sparsity. It encourages the best match with an equal trade-off between x1 and x2. It encourages all the weights to be small, but none of them to be forced to zero in this way. So in this sense, we might get small weights for almost all of the different values of x or theta, but none of them would be pushed to zero. So I hope that clears up the understanding of how the geometry of the different norms help to regularize in different fashions. See you at the midterm.